hele mooie zaterdagmiddag, zonnige zaterdagmiddag vanuit Eindhoven. Ik sta hier bij het Evaluon, ik loop hier bij het Evaluon. Mijn naam is Mark de Haas. Ik doe een opleiding voor Fonties Tilburg, natuur- en scheikunde, leraaropleiding. Ik heb de opdracht gekregen om een kindervraag te beantwoorden. En die kindervraag die komt zo meteen langs. De kindervraag die moet op een wat makkelijke, begrijpelijke manier uitgelegd worden. Zodat eigenlijk een kind hem ook kan begrijpen. Op naar de kindervraag. Hallo meisjes, hoe is het met jullie?
Goed.
Ja? Hebben jullie een vraag voor papa?
Ja?
Nou.
Hoe is de wereld ontstaan?
Dat is God geweest, natuurlijk. Of niet? Nee. Dat is een niet zo wetenschappelijke uitleg. Het is wel een moeilijke vraag. Want wat bedoel je eigenlijk precies daarmee? Is dat de aarde zelf? Of het zonnestelsel? De Melkweg? Of het hele universum? Voor deze vraag moeten we eigenlijk terug. Heel ver terug. Zo'n 14 miljard jaar geleden. Naar het allereerste begin. Het ontstaan van het universum.
Our first threshold is the Big Bang, which happened about 13.7 billion years ago and led to the creation of the entire universe. We don't know much about the ingredients and the Goldilocks conditions that led to this first threshold because we just don't have much evidence. For example, what made the Big Bang possible? We don't know. Why did the Big Bang happen? We can only speculate. Was there even space and time before the Big Bang? We don't know that either. What we do know is that the Big Bang provided the raw materials for everything around us today. After the Big Bang, there was space, which was rapidly expanding, and there was time. There was also matter and energy. At first, the universe was so hot that you couldn't tell the difference between matter and energy. But within the first billionth of a second after the Big Bang, matter and energy separated. Then, energy took different forms, including gravity and electromagnetism. And matter appeared in the form of electrons and quarks soon linked up to form protons and neutrons. Why is this so important? Because nothing had turned into something. And that something contained everything needed to build an interesting universe, one that could eventually include you and me.
Dus het universum is ooit 14 miljard jaar geleden ontstaan, uit het niets. En hoe het ontstaan is en waarom, dat kunnen we nog niet verklaren. Misschien wel nooit niet. Maar dat die ontstaan is, dat weten we in ieder geval zeker. En hoe oud dat het universum is, weten we ook. Alleen verklaart nog steeds niet de wereld om ons heen. Want de allereerste bouwstenen, die protonen, oftewel waterstof en een beetje helium en lithium, daaruit bouw je nog steeds geen aarde op. Want het was voornamelijk gas. Daarvoor hadden we iets anders nodig. Dat is het universum dan. Grote materieomzetters. Oftewel machines die zwaardere elementen kunnen maken. Sterren.
Nebulous house baby stars in every spiral arm of the galaxy.
These regions are the nurseries for new stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink. Stars are made out of gas, basically, and our galaxy has gas. In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk. And it's from this gas that new stars are born.
By observing nebulas at different stages in their evolution, the story of a star's birth begins to emerge. It all starts inside a cold, dark cloud of dust and hydrogen gas, where a quiet tug of war begins. The cloud wants to dissipate, like smoke in the air, but gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. gravity wins, and the material crunches down into a disk that is the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it gets denser and denser and hotter and hotter. Until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium, and with a burst of nuclear energy, a star begins to shine.
These stars eventually get their nuclear fires going in the core, and when they do, they heat up. They can expel the material that's around them so that it kind of clears up the neighborhood.
Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns.
It blows away the gas, it blows away the dust, and it lets us see this beautiful new thing, this place where the star has been born.
A human lifetime is too short to witness the wonder of a star's birth in the spiral arms. But by speeding up millions of years of cosmic time into just a few seconds, we can see one star born after another. Here and there are even more brilliant flashes of light, coming from some of the most violent and dangerous neighborhoods in the entire Milky Way galaxy. Here, stars aren't born, they die.
We zien dus nu de eerste wat zwaardere elementen op de kaart verschijnen. Koolstof, stikstof, zuurstof en dergelijke worden nu al gevormd in wat zwaardere sterren. Dat verklaart nog steeds niet waar de zwaardere elementen vandaan komen. De echte bouwstenen, zoals ijzer en dergelijke, en alles wat er nog boven zit, die zijn gevormd op een andere manier. In supergrote sterren.
As the late great astrophysicist Carl Sagan put it, we are made of star stuff. We are a way for the cosmos to know itself. Whoa, it's an amazing idea, but it's not a metaphor. Many of the atoms that make up you and everything else in the world were literally forged in the nuclear cores of stars. You've seen the periodic table in chemistry class, but where did the elements on that table come from? For centuries, the thinking was that they didn't come from anywhere. They were just as old as the universe and they just simply existed. Later, scientists reasoned that elements originated from the Big Bang. After all, they thought it made sense that the explosive pinprick that started everything 14 billion years ago would also spew out all the elements. That is, up until about 60 years ago. For more, we talked to best-selling author and periodic table superfan Sam Keen.
But in the late 1950s, a group of scientists came up with an interesting alternative. They suggested the universe was once a sea of hydrogen with a smattering of helium and lithium. Eventually, hydrogen atoms clumped together into stars, and the extreme gravitational pressure inside these stars began fusing hydrogen atoms into helium atoms, the reaction that lights up every star in the sky.
All right, cool. So we've got stars in our new universe, but after a few billion years, those stars begin to run out of hydrogen fuel. Once this happens, stars lacking hydrogen fuse helium in their cores instead. Sometimes helium atoms stick together and form even-numbered elements. Sometimes helium gets split up and its protons and neutrons break off to create odd-number elements. So our stars have switched to burning off helium instead of hydrogen. And, well, why don't we have Sam explain what happens next?
After a few 100 million years, stars deplete their helium supply. Some die, but bigger, heavier stars, we're talking at least 8 times more massive than the Sun, move on to crush carbon together into 6 more elements, up to magnesium.
All right, by this point, the stars are burning hot, and by hot, I mean hot. The biggest stars are burning around 5 billion degrees. So, as the stars burn, this snowball effect where stars burn off lighter elements and start fusing heavier ones together keeps on rolling. Eventually, a stable version of every element up to number 26, iron, is out there in the universe. So where does this leave elements 27 through 92? Scientists suspect they come from mini Big Bangs that happen when those big heavy stars die.
As they burn through elements such as magnesium and silicon, extremely massive stars, at least 12 times the size of our sun, burn down to iron cores in about 1 Earth day. But before perishing, there's an apocalyptic death rattle. Burned out stars implode under their own immense gravity, collapsing thousands of miles in just seconds. Then, rebounding from this collapse, they explode outward, and I mean explode. For one glorious month, these supernovas stretch millions of miles and shine brighter than 1 billion stars. Every natural combination of element and isotope spews forth from this particle blizzard.
So why should you care where all that stuff on that periodic table came from? Well, without the nuclear furnaces in the sky to create carbon, oxygen, and nitrogen from hydrogen and helium, and without those massive explosions, Earth and, well, you would never have been formed to watch this awesome video. Do you love this video? You want more?
Nu zijn we een hele stap dichterbij gekomen, een flinke stap. Nu zijn eigenlijk alle elementen die wij zo wat kennen, die zijn nu dus gevormd uit een supernova. Oftewel een explosie van zo'n grote ster. Voldoende groot, zeg maar, om dat teweeg te brengen. Alle bouwstenen voor de vorming van de aarde zijn nu aanwezig. Alleen, hij moet nog gevormd worden uit deze, ja, zeg maar, schrootmateriaal. De restanten van deze ster. Die ooit, zeg maar, zo'n 9 miljard jaar geleden ontploft is. En hoe het zonnestelsel nu gevormd wordt, gaan we in het volgende stukje zien. Kijk maar even.
So, about 9 billion years after the universe was born, in our tiny corner of space, a massive star had already exploded a colossal amount of enriched chemicals everywhere. From this cloud, gravity began its work again. The particles attracted to each other in a now familiar pattern, and the pressure increased until the temperature reached 10 million degrees Celsius. And around 4.5 billion years ago, our sun lit up. Now, luckily for us, some, about 0.1% of the matter surrounding the sun, was not pulled in, but was caught in the pull of its spinning motion. This flattened the debris into rings surrounding the sun, which then collided and pulled together into larger planet-like structures that orbited the sun, but had enough orbital energy to avoid its gravitational pull. From one of these orbits, the third from the sun, our planet Earth was born. From 4.5 to 3.8 billion years ago, the Earth suffered heavy interstellar bombardment, which along with radioactive elements and pressure turned it into a molten furnace, in which most of the heavy elements such as iron and nickel sunk into the core, and the lighter ones floated to the top. Around this time, a large planetary object about the size of Mars collided with the Earth and broke off a segment to create our moon. best place to be. The atmosphere was mostly nitrogen, water vapor, and carbon dioxide spewing out of volcanoes. But as the debris from the creation of the solar system reduced, and with a little help from the enormous gravity pull of Jupiter, the hellish conditions subsided. Water vapor in the atmosphere cooled and rained down on the Earth to form the very first ancient oceans. And the crust formed a solid area of land known as Pangaea. Over time, this land will be forced apart by the large plates, a bit like the pieces of a broken clay plate, that would form the continents we now know today. So, the early Earth, bathed in light from a sun weaker than today, and with a moon much larger in the sky, a hive of volcanic activity caused by pressures from shifting crusts, and an atmosphere that tinged everything red, was ready to undergo a most amazing accomplishment: to produce life.
En daar is ze dan, de aarde, geboren 4,5 miljard jaar geleden. Samen met een hoop andere planeten draaiend om de zon. Uit de restanten van de schroothopen van een supernova. Dat is toch eigenlijk wel hoe de wereld zeg maar, om ons heen gevormd is. En dat we allemaal producten zijn van een restante van een supernova. Wij mensen en de aarde om ons heen. Ik wil nu verder afsluiten met deze video met een ode aan een astrofysicus, kosmoloog, een wetenschapper, groot wetenschapper die helaas is overleden in 1996. Waar ik eigenlijk mijn passie en mijn interesse voor natuur en scheikunde aan te danken heb. En dat is Carl Sagan. Begin jaren 80 heb ik een documentaire gezien, tenminste de 13-delige documentaire Cosmos, die inmiddels een remake heeft gemaakt, Cosmos Space Odyssey, ook een aanrader. Maar dankzij deze man, Carl Sagan, is voor mij de interesse in zowel geschiedenis, want hij behandelt ook veel geschiedkundige aspecten, de wetenschappers die ons voor zijn gegaan, de reuzen, waar wij nu op de schouders van staan. En samen met de wetenschap. Daar is mijn interesse vandaan gekomen. Ode aan Carl Sagan.
The lives and deaths of the stars seem impossibly remote from human experience, and yet we're related in the most intimate way to their life cycles. The very matter that makes us up was generated long ago and far away in red giant stars. A blade of grass, as Walt Whitman said, is the journey work of the stars. The formation of the solar system may have been triggered by a nearby supernova explosion. After the sun turned on, its ultraviolet light poured into our atmosphere, its warmth generated lightning, and these energy sources sparked the origin of life. Plants harvest sunlight, converting solar into chemical energy. We and the other animals are parasites on the plants, so we are, all of us, solar-powered. The evolution of life is driven by mutations. They're caused partly by natural radioactivity and cosmic rays, but they are both generated in the spectacular deaths of massive stars thousands of light years distant. Think of the sun's heat on your upturned face on a cloudless summer's day. From 150 million kilometers away, we recognize its power. What would we feel on its seething, self-luminous surface or immersed in its heart of nuclear fire? And yet, the sun is an ordinary, even a mediocre star. Our ancestors worshipped the sun, and they were far from foolish. It makes good sense to revere the sun and the stars, because we are their children. We have witnessed the life cycles of the stars. They are born, they mature, and then they die. As time goes on, there are more white dwarfs, more neutron stars, more black holes. The remains of the stars accumulate as the eons pass. But interstellar space also becomes progressively enriched in heavy elements, out of which form new generations of stars and planets, life and intelligence. The events in one star can influence a world halfway across the galaxy and 1 billion years in the future.